So, something to point to. Let's talk about Cauchy-Euler equation. What is this about? So, the two methods we just discussed, that is the undetermined coefficient and variation of parameters, were used to solve higher order differential equations, non-homogeneous, of course, uh, with constant coefficients. Now we're going to look at a method where we're going to solve higher order linear differential equations with variable coefficients. All right. So, well, let's go back to the auxiliary equation. So it turns out that the function that we're going to use as a test function, like we did with the previous method, it's going to be different. Okay, so we have the equation of this form, this generic equation. So ax squared y double prime plus bx y prime plus c y equals to 0. What I would like you to notice about this equation is the exponent of the variable, it's the same as the order of the derivative. The order of the exponent is the same as the order of the derivative. All right. And well, in this case, we're going to consider a solution of the form y equals to x to the m. All right. So, I mean, not e to the mx like we did initially with the constant coefficients. All right. In a similar way we did back then, let's find the derivatives. Y prime, that's mx to the m minus 1, and y double prime, m times m minus 1, y to the m, x to the m minus 2. What are we going to do here? Let's substitute this into the differential equation. All right. So that means ax to the, so this will be ax squared y double prime. What's y double prime times? That's m times m minus 1 x to the m minus 2 plus bx y prime. But what's y prime? M x to the m minus 1 plus c y, which is simply x to the m. Okay? And let that be equal to 0 for now. All right? So what about this? So actually, let's simplify this equation. There's a lot we're going to do here. So number one, ax squared times m minus 1 x to the m. But do you guys agree that this is the same as saying x to the m times x to the negative 2? Okay? Plus bx m x to the m times x to the negative 1 plus cx to the m equals to 0. Why are we doing this? Because you may not want to mess with negative exponents, right? So this cancel out, this simplify, leaving us with the following. Okay, so that leaves us with am, okay, times m minus 1 x to the m plus bm x to the m plus c x to the m power equals to 0. How about we factor out this x to the m? All right, factor x to the m, okay? That'll leave us with am times m minus 1 plus bm plus c, and let that be equal to 0 still. Okay? Okay. To simplify the equation inside, or well, the expression inside the brackets. So for this, I'm going to distribute am, so that's x to the m power. That's am squared minus am plus bm plus c. Let that be equal to 0. And guys, do you guys agree that the quantity inside or the expression inside the bracket looks like a quadratic equation where the dummy variable this time is no longer x, It's m. Did you see it? Did you see the quadratic pattern somehow? Okay, even better. How about x to the m? That is a m squared plus b minus a m plus c. Okay, and let that be equal to 0. Does that look like a more standard quadratic equation with leading coefficient a, middle coefficient b minus a, and constant term equals to c? And guys, remember when we did the exponential one, what did we do? Okay, x to the m equals to 0, and am squared plus b minus a m plus c equal to 0. This will be our auxiliary equation. Okay, let me put name to this. Auxiliary, auxiliary, or characteristic equation. So just to compare and contrast these equations, what did we do with linear higher order differential equations with constant coefficients? We just turned them into a very straightforward polynomial, and we solve whatever method, factoring or rational root theorem, etc. Here we need to do a little bit of work before we get that characteristic equation. All right. Okay, and guys, because we are going to solve a quadratic equation here, guess what? We still have three cases: distinct roots, repeated roots, and complex roots. How do we write those results when we have case one, real and distinct? Okay, so C1 x to the m1, C2 x to the m2, just like C1 e to the m1x plus C2 e to the m2x, very similar. However, in terms of x to the power m, when we have m1 and m2 repeated, real and repeated, C1 x and x to the m sub 1, but in this case, C2 x to the m1, which is repeated, gets multiplied with ln of x. All right. In case number three, when M1 and M2 are complex, we go x to the alpha, where alpha is the real part of the imaginary root, and then C1 cosine beta ln of x plus C2 sine beta ln of x, where beta will be the imaginary part of the complex number. So guys, all it changes, it's the form of the solution. The mechanics, the idea, it's going to work exactly the same, very similar. All right, guys, how about we look at some examples? Okay, solve each differential equation below. X squared y double prime plus xy prime minus 9. Okay, let's identify the way we're going to do these equations. This is going to feel a little bit like learning learning how to solve quadratic equations for the first time when we used to write a equals to 1, b equals to also 1, and c equals to negative 9. All right. So let's write the what's it called? The am squared plus b minus a. Let's write the characteristic equation I meant to say. And well, a, which is 1, this is m squared. Okay, that's 1m squared plus, what's b? That's 1 minus a minus 1 m plus c, which is negative 9, equals to 0. All right. Well, 1m squared is simply m squared plus 1 minus 1 is that 0. The linear term disappears. And then plus negative 9, that's actually minus 9, equal to 0. All right. Do you see the form of the characteristic polynomial or auxiliary polynomial? It's totally different, guys. Check. You may think it would have been something like, oh, m squared plus m minus 9m minus 9. This is not how we're going to go. This is the polynomial if we were working with a linear higher order differential equation, but with constant coefficients. Here, it's a totally different kind of equation. All right. Again, there's some elements that are similar, but more different elements. Okay, so let's solve this equation. M squared equals to 9. M equals plus or minus 3. So guys, what do we have? Two roots, real and distinct. All right. So this will be y equals to c1 x cubed plus c2 x to the negative 3. Final answer. Right? Final answer. Yes.
What's like the biggest difference between this one and like the other one, like visually, when you're looking at the equation?
The variable coefficients. Back then we just had numbers, constant like a 5, a 3, a 17, 25. No, this time we have variables, right? This time we have variables. Okay, let's do another one. So am squared plus b minus a m minus plus c equals to 0. All right. So a, which in this case, what is that? Is that 2? 2m squared plus b. Be careful here with what b is. So b, which is negative 1, minus 2, minus a, which is 2, m plus c, which is actually minus 2. All right? And let that be equal to 0. Okay. So let's simplify this quadratic polynomial a little bit. So that is 2m squared minus 3m minus 2 equal to 0. And well, we would need to factor a trinomial where the leading coefficient is different than 1. So the double bubble method right away wouldn't work. And guys, let me give you the result to this factoring problem. That'll be 2m plus 1 m minus 2 equal to 0. Whatever method you use is fine. The trial and error or guess and check, however you want to call it, the diamond method, the slip and slide method, the pizza method, you name it, whatever you want to use. All right. So this is m equals to negative 1 half and m equals to 2. All right. So we got this, right? So y would be c1 x to the power m1, which is negative 1 half, plus c2 x to the power m2, which is 2. All right. Yeah, some factoring, some solving polynomial equations. Again, that's involved. Those are going to get back. Right? Those get back here. All right. What about, okay, am squared plus b minus a m plus c equal to 0. So again, let's have a look at what's a. Well, in this case, a is an invisible one. You guys agree with that? M equals to 1, m squared, I mean a, not m, a, plus b minus a. That is b, which is 3, minus a, which is invisible 1 coefficient, m, plus c, which is invisible 1. Let that be equal to 0. So what do we have? M squared plus 2m plus 1 equals to 0. And what about factors of 1 that add up to 2? Actually, is that m plus 1 times itself? What do we have? Repeated solution, right? We have the repeated case. So m equals to negative 1 repeated. Okay. Now let's see. So what do we have? For the repeated case, let me go back to the three cases at the bottom of the previous page. So That's going to be C1 x to the m sub 1 plus C2 x to the also m sub 1. But because it repeats, to avoid the repetition, we're going to multiply by ln of x. Back when we have the exponential solutions in the previous method, we just multiply by a power of x. Here we're multiplying by a power of ln of x. All right. Okay, let's keep going. Let's write down the solution. So this will be y equals to c1x to the first power plus c2 x to the also first power, which is actually negative 1, right? Negative 1, ln of x. All right. And what about this? That is y equals to simply c x to the negative 1. Oh, actually, that's fine. We don't need to rewrite anything else, right? So that is our final answer. Maybe you want to write the x's in the denominator, but that's fine. There is no need for that. All right. Okay, let's do another one. All right. A fourth example, one more. So this would be am squared plus the quantity b minus a m plus 13 equals to 0. All right. And what do we do? Okay, so a, which is 1, this is simply m squared plus what's b? Be careful. That is negative 5 minus a, which is 1, m plus, oh, I already wrote the 13 here. Should have wrote c. Okay, 13. Kind of spoil it, right? And then let that be equal to 0. All right. So this is m squared minus 6m plus 13 equal to 0. So the question here is, are there factors of 13 that add up to negative 6? So hopefully we can solve this problem by factoring. No, the only factors of 13 are 1 and 13 because it's a prime number and no combination adding or subtracting would give us negative 6, all right? So m, let me use quadratic formula for this. So m equals minus 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 13 minus 4 AC part. Everything divided by 2 times 1. All right. Okay, let's simplify all this madness inside of the radical. That is m equals to negative 6 plus or minus the square root of 36 minus 13 times 4. Yes. Oh, yes, that becomes positive, right? Because minus negative b, right? Yes, you're right. I mean, minus b, which is minus negative 6. Yeah, thank you. And let me change that here too. Hmm? Well, actually, let me do this. Negative, negative, right? To make more sense about it. And then, yes, becomes positive. So 13 times 4, is that 52? Divided by 2, which is 6 plus or minus the square root. 36 minus 52, is that negative 16 over 2? Well, we're going to get nice numbers. M equals to 6 divided by 2, which is, what is that? Well, let me actually do the following. 6 plus or minus the square root of negative 16. Well, the square root of 16, which is 4, because negative 4i divided by 2. 6 over 2, is that equal to 3? 4 over 2, divide equal to 2. All right. So what we have? Complex solutions where alpha equals to 3 and beta equals to 2. What did it look like when it came to complex solution? Well, let me go to the bottom of the previous page. Well, so we're going to have a combination of cosine and sine along with its corresponding constants of to determine depending on the initial condition. Beta will multiply the angle times, which involves a natural log, and everything gets multiplied by x to the alpha. In a similar way, we have the exponential multiplying the combination of cosine and sine. All right. So let's see. Oops. So this will be y equals to x to the alpha c1 cosine beta ln of x plus c2 sine beta ln of x. Okay, which is y equals to x to the alpha, that is x cubed, c1 cosine 2 ln of x plus c2 sine 2 ln of x. All right. Again, it's very formulaic. In all your factoring techniques or methods of solution to polynomial equations, they're going to go back. But the equation we solve, it's going to look slightly different. All right. Okay, let's see what else do we have. Okay, so what if we have a non-homogeneous Cauchy Euler equation? So examples A through D were examples where the right-hand side of the equation equals to 0. Well, what about the non-homogeneous Cauchy-Euler equation? Well, so guys, in this case, we will have to use variation of parameters, all right? Do not attempt to use undetermined coefficients because undetermined coefficients, those are constant values on the homogeneous part of the problem. Here, what do we have? Variable coefficients. So don't even attempt, right? So let's solve one example. Let's go about one example. So let's write the characteristic equation for the homogeneous part of the problem. Okay, so that is am squared plus b minus a m plus c, and let that be equal to 0. Right? So a, which is 1, that's m squared, plus b, which is 1 minus 1, all right? M plus, actually, okay, yes, plus negative 1 equals to 0. So m squared, 1 minus 1, is that equal to 0? That cancels the linear term, leaving us with minus 1, all right, equal to 0. So m squared equals to 1, and m equals plus or minus the square root of 1, which is plus or minus 1. The first thing we do is write our, what is that? Our y equals to c1, okay? C1 x to the first power plus c2 plus c2 x to the negative 1 power, which is the same as saying c1 x plus c2 x to the negative 1. All right? Okay, guys, from here, what do we get? y1 equals to x. And from here we get y2 equals to x to the negative 1. All right. And that's because we're going to evaluate the Wronskian. y1, y2, y1 prime, y2 prime. Okay. So y1, y2, that is, what is that? Okay, so x, x to the negative 1. Find the derivatives of these two functions. That is 1 and negative x to the negative 2. Okay. And now compute the Wronskian. Evaluate the determinant. So x times x to the negative 2. Let me indicate x times negative x to the negative 2 minus 1 times x to the negative 1. Okay, what do we get when we multiply x with x to the negative 2? So invisible power 1 plus a negative 2, isn't that negative 1? So that's negative x to the negative 1 minus 1 times x to the negative 1, which is also x to the negative 1. But these two guys are like terms. That is negative 2 times x to the negative 1. All right? So now let's evaluate the two integrals from variation of parameters to get the combination u1, y1, u2, y2. Okay, so u1, what's u1? Oops. So u1 equals the integral of y sub 2g of x over the Wronskian dx, which is the integral of what was y sub 2, x to the negative 1, okay, times g of x. What's g of x? G of x, 4x ln x, okay, 4x ln of x, uh-huh, where, oh, not yet, not yet. We need to go back and do something interesting here. Because, guys, the form of the equation before, and that's I fell in my own trap actually. Okay, so yeah, before you attempt to evaluate these integrals, first thing you need to do is make sure the highest order derivative term has a coefficient equal to 1. What do we do in this case? Divide both sides by x squared. This will give us, well, I don't care actually about the left-hand side. All I care is g of x equals 4 over x squared. Is that 4 ln x over x? Right? And that's what we will input into the integrals. All right? Okay, so what is that? That is y sub 2, which is x to the negative 1, times g of x, which is 4 ln x over x, divided by the Wronskian, which is negative 2, x to the negative 1. And oh, there's a bunch of negatives going on here and a lot to simplify. Okay, number one, negative divided by negative, that's positive. 4 divided by 2 equals to 2. So, oh, don't forget the dx. So this is 2 outside of the integral. And also, check this out. Um, this will be, okay, let me also cancel x to the negative 1 with x to the negative 1. Okay, and this will be ln of x divided by x dx. All right, and to evaluate this integral, okay, what do we do to evaluate this integral? Would a u sub work? Yep, u equals ln x, du equals 1 over x dx. And oh, we have the dx over x, right? Uh, Actually standing for the du part of the problem. So, and no compensation factor. So that's still integral of u du, which is the integral of 2u essentially is u squared, and back substituting, we get ln of x quantity squared. Be careful. Ln of x is not, ln of x quantity squared is not the ln of just x squared. Yes.
Going back to the Wronskian, if we
Yes. Okay, good question. If we reverse the order of y1 and y2, yes, we would get initially the Wronskian with the opposite in sign. But keep in mind that when we compute u1 and u2, they are also opposite in sign, so we will have a compensation with the signs at the end. So it doesn't matter if you do the other way around. You should get the same overall result. Okay, what's u sub 2? U sub 2 equals the integral of y sub 1 g of x over the Wronskian dx equals to, what was y sub 1 was x only? Yes, it was x, and then times 4 ln of x over x divided by x to the negative 2, x to the negative 1. All right. Okay, so that's the dx. So actually, number one, cancel x with x right here. What is that going to leave us with? Well, that's 4 divided by 2, and it's also negative 2 outside of the integral Also, what about this x to the negative 1 in the denominator? We can move it to the numerator with positive exponent, leaving us with x ln of x dx. To evaluate the integral we have over here, we would need integration by parts. I'm just going to give you the result, all right, to keep this quick. So negative 2 times x squared over 2 ln of x plus, or minus rather, minus x squared over 4, all right? So again, use integration by parts to evaluate this integral. So what do we have? Oh, let's reduce the coefficients. That's x squared ln x minus minus equals to plus. Oh, first one's a negative. X squared over 2. All right. So what do we do? Let's form y sub p. Y sub p equals to u1 y1 plus u2 y2 equals, okay, u1. What did we get? What did we get for u1? ln of x quantity squared y1. But what's y1? Isn't that just x plus u2, which is all this madness here? And I'm going to write, okay, yeah, negative x squared over 2 ln of x plus x squared over 2 times y sub 2, which is x to the negative 1. Yes.
Is the ln x squared supposed to have a two?
Which one? Here
The u1.
for the u1? Yes, this one right here as an exponent. Oh, do you mean oh, as a coefficient? Oh no, not anymore because these two, that was actually 2u. What's the integral of 2u? U squared, right? Right? So it actually was used as a compensation factor, so to speak. Okay. And what do we do? What do we do next? Okay, y sub p equals to so x parentheses ln of x squared. Over here, check this out. X squared times x to the negative 1, subtract 1 to the exponent. That's actually negative, uh, negative x, okay? Negative x to, okay, over 2 ln of x. And over here, plus x squared times x to the negative 1. Is that x over 2 also? All right? Okay. So finally, y. Okay, do we have anything to simplify? No, I believe that's about it. Okay, so y equals y sub c plus y sub p, which is the complementary solution c1 x plus c2 x to the negative 1 plus the particular solution, which is all that madness there. All right, that is x ln of x quantity squared minus x minus 1 half x or x over 2 ln x plus x over 2. All right. However, we have another problem here. Well, not a problem. We have something interesting. So do you guys agree this guy, it's a duplicate? These two are duplicates because they are the same variable, the same term essentially with a different coefficient. One is an unknown coefficient, the other one is known coefficient, so we can absorb them together. All right. So y equals to c1x again plus c2 x to the negative 1 plus x ln of x squared minus 1 half x ln of x. Final answer, perfect timing.